Welcome back to the Learning Studio. You're watching our mathematics series, where we uncover the hidden pillars that make science, technology, and artificial intelligence possible. If this is your first time here, don't forget to follow us by clicking the link below. And remember, the full playlist is also in the description, so you can explore every episode step by step. Today, we're tackling one of the most rigorous and abstract fields in mathematics: measure theory and probability spaces. It may sound intimidating, but it's the foundation that makes probability, statistics, and machine learning truly solid. Here's the problem. Early probability theory worked well for dice, coins, and cards. But what about continuous events, like the probability that a randomly chosen point lies inside a circle? Or the probability distribution of infinitely many outcomes, like stock market fluctuations? Classical probability struggled with these questions. Enter Andrei Kolmogorov, a mathematician in the 20th century, who rebuilt probability from the ground up using measure theory. His framework finally gave probability a rock-solid foundation, one that modern data science and AI still rely on today. Here are the key ideas. Measure theory. At its core, measure theory is about assigning sizes to sets. Length, area, and volume are measures we know well. But measure theory extends this idea to far more complex sets, even infinite ones. Sigma algebras. These are collections of sets that allow us to talk consistently about which events are measurable. They're the rules of the game for probability. Probability spaces. A probability space is made up of three parts: a sample space, all possible outcomes; a sigma algebra, the events we care about; and a measure, the probability assigned to each event. This is the rigorous definition of probability. Integration in measure theory. Instead of simple sums or areas under curves, measure-theoretic integration allows us to calculate expectations and averages in a consistent and general way, even for random variables that are continuous or infinite. Why it matters in AI and technology. Measure theory might sound abstract, but it's the backbone of many real technologies. In machine learning, probability distributions over continuous spaces require measure-theoretic tools. In stochastic processes, like Markov chains or reinforcement learning, measure theory ensures rigor. In Bayesian inference, integration over infinite parameter spaces depends on these ideas. Even deep learning relies on probability spaces when analyzing convergence and generalization. Without measure theory, probability would be shaky. With it, we have the precision to build everything from financial models to modern neural networks. So measure theory and probability spaces are the mathematical foundation of uncertainty. They ensure that probability isn't just intuition, but a rigorous science, one that underpins AI, data, and the randomness of the real world. In our next episode, we'll build on this foundation with functional analysis, a field that connects infinite dimensional spaces, neural networks, and kernel methods. It's the mathematics that allows us to stretch beyond simple numbers into the vast landscapes where modern AI truly lives. Don't forget to follow us by clicking the link below and check out the full playlist in the description. Each episode brings us closer to understanding mathematics as the true engine of intelligence.